All right. So this is one of my favorite example problems of all time. Not because it's actually all that interesting of a problem, to be honest, but because of the person involved. So Abe Baldwin would, if I had a Hall of Fame of engineers or scientists, maybe we can add them both then. Um, but he's definitely an engineer. Abe Baldwin would be the first inductee into it. So let's set the scene. New Orleans in the very early 1900s was expanding rapidly, and it had started as a small fort on a rise hill, essentially at the with it had a lake behind it, Lake Pontchartrain, whatever, and the Mississippi River flowing alongside it, and all around it was marsh. It was a terrible place. And as the city expanded, people kept moving farther and farther into the marsh area, and they would build these canals that would kind of drain the water into the lake behind them. But anytime that the lake flooded or the Mississippi River flooded, those houses would be the first to flood, and it was terrible. Um, it just constantly people flooding. There's disease because everything stayed wet, so it was bad. And the city contracted somebody to design a pump that would be able to dry the city out. And it's an interesting design problem because you only have to raise the water about 2 meters or so because you're trying to raise the water up over a wall, a levee into the Mississippi River, and or into the lake behind the city. But either way, it's not very high um, wall, but it has to have very high flow rates. And more importantly, like any city, um, the the water basically is a trash collector, right? Everything gets swept into these canals and then goes from the canals to these pumps, and then from the pump it goes through the pump, right? And so he designed a very efficient pump that could also basically pass a car tire through it. There's examples of it passing an old bike through it, right? Uh, these pumps are just amazing and revolutionary for their time. And he did it without computers. He just kind of um, eyeballed it. Well, I'm sure he did a lot of experiments and other things like that, but he wasn't able to basically do a lot of food experiment simulations. So it's incredible. It's absolutely incredible. You should read about him. And these kept the city dry up until 2003, I believe it was, when um, when uh, when Katrina came, right? And even then, they would have kept the city dry. It was just that the pump houses lost power, so they weren't able to function. So anyway, we know that these pumps were connected to a 450 kilowatt electric motor, which was amazing for the time as well, but still, and that they were made out of steel, and the roughness of steel is roughly 0.025 millimeters. The flow rate was a phenomenal 17 meters cubed per second. They sold these pumps all over the world with the bragging that two of these pumps together could suck the Thames River dry that flows through London. Uh, and the diameter of these pipes was a huge 3.5 meters. So we are going to assume steady state flow, uniform properties. Remember, we have to because we're using conservation of energy. And our equation that we're going to use is our conservation of energy with our head losses now added in. So we have a P divided by rho G plus V squared over 2G plus Z out is equal to P over rho G plus V squared over 2G plus Z in plus head loss, or H pump, plus sum of all of our head losses. And remember, we say sum because we have minor and major head losses we have to include. Um, yeah. So let's calculate our major head loss first. Major head loss is the first thing we have to do is we have to calculate our Reynolds number. So our Reynolds number is rho v d over mu. We know everything in here. We know diameter, we know mu. We don't know v, so let's calculate v. So equation 2 is going to be v is equal to q over a, which is equal to 6. Did I say 16 or 17? I said 17 meters cubed. 17 meters cubed divided by the area, which is pi times 3.5 meters squared divided by 4, which gives us a velocity of 1.66 meters per second. Yeah, 1.66 meters per second. So with we can plug that now into our Reynolds number, and we find out that our Reynolds number is equal to 1,000 kilograms per meter cubed times a velocity of 1.66 meters per second times 3.5 meters. All of that divided by 1 times 10 to the negative third kilograms per meter second. We find out that our Reynolds number is equal to 5.8 times 10 to the sixth. We get in E over D, we plug everything in, of 0.025 millimeters divided by 3.5 times 10 to the third millimeters is equal to 7 times 10 to the negative sixth. Now you again see one of the advantages of using a very large pipe, namely that the roughness matters less and less and less. So those pipes feeding water to New York City, another reason to have just a gigantic pipe is that you can use concrete, and the roughness of the concrete is negligible compared to everything else. So we have a very small roughness, and use your preferred method of solving for our friction factor, be it Moody chart, implicit or explicit equation, and do that now. Solve for it. Pause the video, do it, and then hopefully you return, and then I'll tell you. So, all right, now I'm going to tell you because I assumed you paused it, and it's equal to 0.01. So that's our friction factor. So we also have a minor head loss, which is a reentrant entrance, where the K is equal to 0.78. The way I've drawn it, we just have our pipe sticking in the water. So that gives us, when we go up to our equation now and we simplify it, we're going to draw our control volume so that we're at the top of the canal. We come in through the pipe and we exit up to the top of the exit. Okay, so effectively at our entrance and our exit, our fluid velocity is 0. Our pressure is 0 because it's gauge pressure. In fact, let's write that down so that our graders know. And yeah, and our Z in is going to be 0 because of how we drew our coordinate system. So our Z out then is equal to H pump plus H losses. So if we write that out, we see that 2 meters is equal to H pump minus our sum of our head losses. And our sum of our head losses is going to be equal to this is going to be equal to F L over D times V squared over 2. But so we also have our minor loss coefficient. So we're going to say plus KL times V squared over 2G, just so we can do a little bit less algebra, a little bit less math. And so when we plug that in, we get 2 meters is equal to HP minus 0.01 times 25 meters divided by 3.5 meters, or length of our pipe divided by diameter, plus our minor loss coefficient, 0.78, times our velocity squared, 1.66 meters per second squared divided by 2 times 9.8 meters per second squared. Great. So we know everything in here now, and you'll note that we subtracted this, right? And unfortunately, all of the equations for minor loss in your book are going to be positive, and you know that minor losses, any losses, subtract energy from your system. So you have to explicitly put that minus sign in order to subtract it. So we subtract this energy, right? And we solve for HP, and we find out that our H pump is equal to 2.12 meters, which is fantastic because if you think about it, we're raising the fluid up 2 meters, and that means our losses are only equal to 1.12 meters, which is pretty good system. So our W dot pump is equal to divided by G M dot is equal to HP. So if we say that our W dot pump, capital W dot pump, is equal to HP times G times M dot, when we plug all that stuff in, we get 2.12 meters times 17 meters cubed per second times 1,000 kilograms per meter cubed times 9.8 meters per second squared gives us a WP of 352 kilowatts. Which if we calculate our efficiency then, N is going to be equal to, is going to be equal to W dot pump divided by W dot N. We know that this is 400, what did I say it was? 450 kilowatts. This is 450 kilowatts. And we know that W dot pump, we just solved for it, is 352 kilowatts. So our efficiency is 0.78, which is frankly not bad at all. Not bad at all. Yeah. Again, just an incredible engineering feat, and it really changed the lives of millions and millions and hundreds of millions of people around the world. Cool. All right. So our next video is going to be a group quiz, not quiz. We're going to imagine that you can attach a new 600 kilowatt motor to the wood screw pump. Same pump, new motor, and we will assume the efficiency remains the same. That's not going to be true, but we want to know what the new flow rate is. And it turns out this is an iterative problem because we need V to solve for our friction factor, but our friction factor depends on V, and so now we have an implicit problem, which means we have to solve it iteratively. And we will talk about how to do that in our next video.